Okay, so we'll move on to discuss some other things to do with energy and potential. Okay, so first I'd like to do a small correction for last video. When we talk about electric field, right, it's 1 over 4 pi epsilon naught Q over R squared, right? So I missed out the square in the last video. Okay, so just take note of that. Okay, we move on to some special cases. Alright, when we talk about parallel plates, okay, we realize that parallel plates, there's something special about parallel plates in the sense that the electric field within the parallel plates is a constant. Right, so if the electric field within the parallel plates is constant, then the electric field can be calculated by a special formula, E equals to delta V over D. Right, this formula is actually a special case of this formula over here. Right, it's actually a special case of this one. This one is the general formula. Okay, there are a couple of general formulas here. Okay, we can talk about it a little bit. Okay, this is a general formula, this is a general formula, this is a general formula, this is a general formula. Okay, these four formulas over here, okay, maybe I'll asterisk it, are specific formulas. Okay, what are specific formulas? That means these four formulas are only valid for point charges. Alright, I can only use this fourth formula, QQ over R squared, where I'm dealing with 2-point charges. Okay, I can only use this formula when I'm talking about electric field strength for a point charge exerted around it, right, and so on and so forth. These four formulas only involve point charges. These four formulas that are ticked are used in all cases. They can be used in all cases. Alright, so these four are general formulas. They can use in all cases. So if I look at this special scenario over here, whereby it's obviously a parallel plate and one charge, right? This is two positions, right? But one charge only. Okay, let's say there's only one charge here, right? So why A and B I'll talk about later, but in any case, this is just one parallel plate and one charge. So there's no way I can use this formula, right? Because there are no two charges. There's no way I can use this formula because this one is talking about electric field due to a point charge Q1, right? That's why I cannot use this formula here. When I talk about the field here, which is this field over here, okay, this is field due to a parallel plate, which has nothing to do with a point charge. Therefore, this electric field here cannot be described using this formula. Okay, so instead, how to calculate electric field? I have to use a general formula from here. Alright, and this one is minus dV dr. So this one applies in all cases, and we'll discuss it in a moment in this graph. Okay, but first let's focus on the parallel plate case whereby this one can be simplified into this one. Right, because for every change in delta D, where D is actually a distance in the vertical direction, right, this is delta D, the change in delta D. For every change in delta D, for every fixed change in delta D, the delta V will be the same, right? So the change in potential per unit length is the same throughout. Alright, that's why I can simplify this formula into this formula. Alright, so this is for parallel plate only. Okay, or when they say electric field is constant. Alright, let's say I have a charge at point A and the charge moves to point B. Okay, what happens to the force, right, at point A and point B? Right, in this case I again have to use a general formula because I can't use this formula. Right, again this for 2-point charge, so I have to use F equal QE, general formula. Alright, so F equal QE, my E is already given by this formula over here. Okay, delta V over D. Okay, I like to use this as delta V to remind you that this is a potential difference. Okay, a potential difference divided by a distance, right? This is in contrast with this case where this is potential at a point, right? So just to make it clear why I put delta V here, this potential difference. Okay, so the force acting on the charge, let's say plus Q at A and at B, is exactly the same because I just need to start the plus Q here, right? And the electric field is the same at all points. So electric field can be given by delta V over D, right? So this is the force acting on A, this is also the force acting on B, right? So there's no difference. Okay, if I move it horizontally, there's also no difference, right? Because again, it's just a simple application of this formula. Right, so let's talk about energy instead, because energy will be slightly more interesting. Energy on the positive charge on AB, on A or on B, right? So if I look at the positive charge at A and I look at the positive charge at B, which one do you think will be higher energy? Okay, I need to use a general formula again, right? So in this case, I will use this formula over here, energy equal to Q times V, right? So maybe I should write E. Okay, normally E is reserved for electric field. Okay, I'm talking about energy in this case. So my U equal QV, okay, which is potential at a point, different from this one, which is potential difference. Okay, so my energy at point A can be given by the charge plus Q multiplied by potential at A. And for B, the same thing, Q multiplied by potential at B. So which potential is higher tells me which energy is higher. Alright, so I'll just replace all of this by U. Alright, so if I look at this thing over here, if this is positive and this is negative, this is a high potential. Right, this is high potential. This is low potential. So B is clearly higher potential than A, right? Because my potential is dropping all the way until I hit the negative aspect. Right, so B is higher potential than A, so when I multiply VB, which is a higher value than VA by the same Q, then obviously the energy due to B must be greater than energy due to A, right, for a positive charge. Okay. However, if the positive charge is replaced by a negative charge, I compare A and B again. Now because this is energy, remember that for this case I have to sub the charge sign. Okay, so just now it was just plus Q multiplied by VA and plus Q multiplied by VB. Now if the Q, positive Q replaced by negative Q, what happens is that this thing becomes negative. So let's say, let's sub some values. Let's say this is 5 volts, right? Let's say this is 0 volts, right? So let's say B is maybe 4 volts and A is 2.5 volts, right? So somewhere in the middle, right? So if Q is 1 coulomb, right, the energy at B will be 4 joules. The energy at A will be 2.5 joules, right? That's why UB greater than UA, because VB greater than VA. However, if the charge becomes negative, right, then this Q will sub by -1, right? So VB, the energy at B will be -1 multiplied by 4, right? Because VB is 4. So the potential energy at B will be -4. Potential energy at A will be -2.5. So which one is bigger? Actually, -2.5 is bigger than -4, right? Because it's a scalar, right? So -2.5 is greater than -4, alright? Hence, actually, energy at A is greater than energy at B. Okay, I'm going to sub hypothetical values here just to assist you, alright, in understanding. Alright, so it's joules. Right, we assume 1 coulomb charge, positive or negative, just to make the calculation easy. Right, so this will be 4 joules and this will be 2.5 joules. Right, we assume that Q plus Q is actually 1 coulomb. So 1 coulomb times 4 volts, right? 1 coulomb times 4 volts gives me 4 joules, so on and so forth, right? So that's how I think about energy, right? Again, we must take care of this idea over here, which is really very important, and actually the crux of the last 2 videos that we've been discussing.